I am Dominik Tornow. I am the founder and CEO of Resonate. At Resonate, we focus our work on distributed async await, a programming model designed to make scalable and reliable distributed applications dead simple. I am also the author of Think Distributed Systems, which is currently part of Manning Publications' Early Access program. And the book focuses on dependable mental models to empower you to reason confidently about distributed systems. So it's fair to say that I spend most of my time on distributed systems. Now, distributed systems are known for their complexity. We all just know that distributed systems are complex. We all just know that developing and testing distributed systems is complex. But what, at its core, makes distributed systems so complex? And there are two reasons, two fundamental sources of complexity. The first is non-deterministic partial order, introduced by concurrency. In a concurrent system, we simply don't know what will happen next. And the second is non-deterministic partial failure, introduced by distribution. So in a distributed system, we simply do not know what will fail next. Now, as an aside, feel free to take pictures throughout the entire presentation at any time, but I have marked some slides as an aha moment to highlight what I think is most insightful. So this is one of these aha moments. Now, let's consider a simple, very abstract example to develop an intuition. So let's argue we have two processes, P and Q, each consisting of just 3 actions, 3 steps. So first, let's introduce sequentiality. The defining characteristic of sequentiality is total order and total application. A sequential system executes one step at a time in a predetermined sequence. So there is the sequential composition of P and Q leads to one possible execution. There is simply no room for any alternatives. Next, let's look at concurrency. The defining characteristic of concurrency is non-deterministic partial order. So the concurrent composition of P and Q already leads to 20 distinct possible executions. And finally, let's introduce distribution. The defining characteristic of distribution is non-deterministic partial failure. So the distributed composition of P and Q leads to 69 distinct possible executions. And in a real system, some of these executions are common, while others are super, super rare. So for example, imagine a scenario where a server accepts a connection at the exact moment a configuration reload is triggered. That is a highly unlikely sequence of events. So if we do a simple thought experiment, given that we have 69 distinct traces, let's assume that 10% of these traces are the happy path. They occur 90% of the time. Right? And all of the rest, 90% of the other traces, they are edge cases. Right? They only occur 10% of the time. If we now non-deterministically pick a trace according to this probability distribution 1,000 times, the chances of missing at least one trace is almost 100%. And these rare traces are the ideal breeding ground for the dreaded Heisenbugs. And the term Heisenbug is inspired by the Heisenberg uncertainty principle in quantum mechanics. Right? Heisenbugs are elusive. The rarity of the trace that hides them makes them hard to produce. And by the off chance we actually do produce them, we cannot reproduce them. Right? We'll never go down the same path. Now take a moment to imagine the behavior space of a real-world distributed system with dozens or hundreds of processes, each with dozens or hundreds of steps. The number of possible executions grows combinatorially, and that phenomenon is aptly called behavior space explosion. But concurrency and distribution, they don't just expand the behavior space. Right? They make reasoning about systems almost incomprehensible. Concurrency and distribution introduce daunting uncertainty. And this uncertainty is a true challenge that we face when we design and develop distributed systems. Now, there is a direct correlation between certainty and confidence. When I am certain about my application, I am confident in my application's correctness. Right? Making changes, adding new features and functionalities, deploying to production on a Friday, no problem. So deterministic simulation testing for me is a key component to achieve this level of certainty and confidence by methodically exploring the behavior space, scaling across both space and time. So throughout the rest of the presentation, we will build a foundational understanding of deterministic simulation testing step by step. We will build a dependable mental model so you can decide with confidence if deterministic simulation testing is right for you and your application. So let's begin by grounding our discussion with a mental model of software systems. What is a software system? For our discussion, we will think of a software system as being partitioned into two distinct entities, the environment and the application. The environment represents everything that is not the object that we are developing in testing. And the application represents everything that is the object that we are developing in testing. Our goal is to test the application. And to achieve this, the application under testing conditions must closely resemble the application under production conditions. Right? Any deviation must be non-material, otherwise we're just testing something completely different. However, our goal is not to test the environment. The environment is only a means to facilitate the test. Therefore, the environment under test conditions does not have to resemble the environment under production conditions at all. We are free to replace, we are free to mock components as we see fit. So how do we delineate between the environment and the application? What's in and what's out? There is no universal answer. When you delineate, where you delineate depends entirely on your requirements. So here we see an example of a web application composed of three distinct components: a client on the left, a web server in the center, and a database on the right. A reasonable choice is to assign the client to the environment while treating the web server and the database as part of the application. Right? The focus is on testing the web server and database server in composition. However, a reasonable alternative is to assign both the client and the database server to the environment and treat the web server as the application. Right? Now the focus is on testing the web server in isolation. Okay, now that we have a mental model of a software system, when is a software system correct? And how do we establish that a software system is correct? Correctness is not absolute. Correctness is relative to a specification. Consistency models offer a fantastic example of this principle. Take an implementation of a distributed key value store. If the implementation allows stale reads, the implementation is correct if evaluated against the specification of eventual consistency, which allows a read to reflect some previous write. But the same implementation is considered incorrect if evaluated against the stricter specification of linearizability, which requires a read to reflect the most recent write. So the same implementation can be considered correct or incorrect depending entirely on the specification that we choose to apply. As Leslie Lamport explores in his foundational work specifying systems, software systems can be understood in terms of state machines. A state machine is remarkably simple, yet remarkably powerful to reason about software systems. A state machine consists of only 3 components: a set of states, a set of initial states, and a next state relation that determines how we transition from one state to the next state. When we execute a state machine, the state machine generates a trace. A trace is a sequence of states that represent the system's behavior over time. And traces are at the heart how we reason about software systems. Each trace represents a unique execution of the system. Now, a state machine is non-deterministic if the state machine presents a choice, or in more sinister terms, ambiguity. So in this example, from S1, we may transition to either S2 or S3. And this is reflected in the set of possible traces given the initial state of S1. Right? In this example, from the initial state S1, we may generate 2 distinct traces, S1 to S2 or S1 to S3. So given the initial state, we may witness different traces. A state machine is deterministic if the next state relation is a function, that is, if the state machine does not present any choice. In a deterministic state machine, there is simply no ambiguity, just one single predictable path forward. And this is reflected in the set of possible choices given the initial state of S1. In this example, from one initial state S1, we will generate only one trace from S1 to S2 to S3. So given the same initial state, we will always witness the same trace. Now, coming back to the specification and implementation relationship discussed earlier, in effect, a specification is a set of traces. And these traces represent all the valid behaviors that are allowed by the specification. So an implementation is correct with respect to a specification if every possible trace of the implementation is also a possible trace of the specification. And an implementation is incorrect with respect to the specification if some traces of the implementation are not traces of the specification. So, how do we actually establish correctness? There are 2 possibilities: software verification and software testing. In software verification aims to prove that all traces of an implementation are within the specification. And software testing aims to find some traces outside of the specification. Okay, so in summary, if the verification asserts the system is correct, the verification asserts that no correctness violation will ever occur. And if the test asserts that the system is correct, the test merely asserts that no correctness violation has occurred yet. So testing is essentially a search problem, where the goal is to find traces of the implementation that violate the specification, that violate correctness. So how can we increase confidence in a system's correctness? By increasing test coverage. Test coverage has 2 dimensions, space and time. To scale across space, we extend our test by extending the number of different traces covered by the test. And to scale across time, we extend our test by increasing the length of different traces. However, extending the number of different traces is very difficult. As we saw in the initial example, just randomly stimulating the system will produce more of the same traces, not distinct traces. And additionally, extending the length of distinct traces is also difficult. Many systems have actual timing constraints, such as timeout around crash detection, or timeout around message loss detection, or the time intervals driving rate limiting algorithms. Increasing the length of a trace increases the actual testing time. Now, deterministic simulation testing enables you to scale across space by controlling the scheduling and failure injection, and therefore increasing the number of distinct traces. And additionally, deterministic simulation testing enables you to scale across time by virtualizing time, and therefore increasing the length of distinct traces while shortening the test time. You can, in effect, squeeze 30 years of traffic into 8 hours of testing. And lastly, deterministic simulation testing enables you to reproduce a trace by ensuring that for every starting state, there is only one possible trace through the system. To be methodical and to ensure reproducibility, we construct the system. That is, we construct both the environment and the application so that the behavior of the system only depends on the initial state of the environment and the initial state of the application. The core idea is to substitute the environment with a simulator. Deterministic simulation testing repeatedly executes an application in a simulated environment under changing initial conditions, monitoring that the correctness constraints are maintained across executions. And in practice, this means constructing the system to control otherwise non-deterministic factors such as incoming requests, but also crashes, message losses, and time. So on a high level, we have to think about two interactions: requests from the environment to the application and requests from the application to the environment. The first represents the application input and output, and the second represents the application's side effect, like talking to the network or reading and writing to the file system. And by controlling scheduling and failure injection in the simulated environment, giving a deterministic application, we can deterministically generate an arbitrary amount of distinct traces at an arbitrary length. Now, who is doing simulation testing today? A few companies and projects have adopted deterministic simulation testing. For example, FoundationDB, TigerBeetle, Polar Signals, Tornow, and my company Resonate. And each project took a different approach in designing and developing its application and in designing and developing its simulator. And additionally, there is Antithesis, the first company offering deterministic simulation testing as a service by implementing their own deterministic hypervisor. If you're curious and you would like to dive deeper into deterministic simulation testing, I wrote a blog post a while ago on the fundamentals of deterministic simulation testing. And additionally, I had a recent conversation with Joran, the founder and CEO of TigerBeetle, a special purpose database for financial transactions, where we talk about writing your own deterministic simulator. Now, deterministic simulation testing requires some investments. However, the payoff is significant. Deterministic simulation testing enables you to methodically test the behavior space of your system by scaling across space and time, making traces reproducible. So you get to squash the bug once you find the bug. And with that, thank you very much for attending my talk, and I hope you have a fantastic conference.
Thank you very much. Are there any questions?
Since the name of it was Heisenbug, it got me thinking about older kind of physics and math. Well, more of a funny question, but Dijkstra, way back when, even before They were even had computers. He wanted algorithms to be provable in the same way that math is provable. Do you think we could ever get there? It seems some of these things are just hardware related, where we just can't say whether it's the system's so complex we just can't. We don't have that level of theoretical proof. But what would do you think we could get to that stage, or we can use that kind of reasoning?
I am highly biased. I'm a big fan of formal methods. I use, for example, TLA plus, or recently also PLang and FISB to formally verify the design of the systems, not the implementation. But I believe that deterministic simulation testing gets as close to formally verify an entire implementation as you can practically get. There are, of course, some other methods, like, for example, Daphne, that is a verification-aware programming language that lets you actually write provably correct code, right? But that investment is significant. So again, I'm a huge believer in formally verifying the design of a system, because there you can raise the abstraction level so high that that is actually feasible. And there you have to design, you have to think about the design envelope. So what failure modes are in, what failure modes are out. But I don't think that anytime soon we will get to actually formally verified implementations. That's where I think deterministic simulation testing can actually practically close the gap.
Thank you. Any more questions?
So that's really cool. I can see how this applies to something like a TigerBeetle or an end product. Once you start mapping this to meshes of microservices like that trace space just becomes infinite. How do you scale that up beyond an end service?
So the scaling, you're entirely correct, right? The state space explosion also basically means that the state space is infinite and we cannot actually enumerate it, right? But so based from my personal experience at my company, even so that the space state is infinite, you can get actually very, very far. So at this point, our deterministic simulation testing finds bugs where we're basically like, oh my God, why are we even fixing this? This is not going to happen in 500 years of runtime, right? So, and we basically have the idea or the notion that if our tests uncover bugs that far out in the edges and fringes of the system, that basically means we can have a very high confidence that the bugs in the center of the system are already eradicated. So while you're correct, there is basically no way to enumerate all traces. My practical experience points at the huge payoff if you run this thing continuously in your CI for a few hours.
Thank you. Any more?
A question about, have you looked into doing this from the other direction? So instead of running the code and doing traces and stuff like that, have you looked into analyzing how the code looks like and what it can and not do, so you can actually try to prove the code that it's right, because it should be, because yeah, of course you cannot simulate the whole thing, it's a combinatorial explosion, but otherwise if you go from the other side, you should be able to cut a lot of this out of the testing and to actually be able to prove that something is correct.
Yeah, so I have recently started to experiment with Daphne, a formal verification-aware programming language, that when you actually construct the Daphne proof, you can be sure that this is correct. It's mathematically proven. Very, very cool, very, very involved. So that is, it is really pulling teeth.
Yeah, one question. I've worked on formal specification of languages for quite some time, and one of the typical patterns to give a formal model of the specification is observable state system, which is probably very close to what the testing space does. Do you think it's possible to go back and forth between the two? Because the information you get from deterministic testing could show you parts of a proof that, well, needs to be fixed, or a proof that is incorrect. I mean, we know that not all proofs are correct. Or also go the other way around. If a proof, you try to prove something formally, you should actually get also a trace that on the test site that exhibits the incorrect behavior.
Short answer, yes. So yes, I think that is possible. As far as I know, large companies like, for example, Amazon and AWS are actually employing something like that. I have no personal experience with that, but based on the formal specification of the system, they generate traces, right, out of the formal specification of the system, and then feed that trace after a translation step. Feed that trace into the system and check if that trace is also a valid trace of the system, therefore closing the loop in the other direction. Very, very cool stuff.
So you have to have your own formal specification language in your system then too.
Yeah, basically.
And Dominik will be around, so please, you can catch him in the hallway track outside after this. Thank you very much, Dominik.
Thank you very much.